So how many of you have had a chance to try those structures that I sent out? Have you tried them at all to solve? They were on the website. You put them on the website, right? So there were some practice structures there. None of them are difficult. They're just for practice. So I have made some drawings of the results, but I haven't put the res files on here because they don't look particularly interesting on the computer. But if you need the res file, let me know. But I have some graphics that show the results. It's just for practice if you're interested. So there was a request to talk a little more about part, and I think that's a good request. I think we should. It's a source of a lot of confusion, and like I said, some people have way too many parts in their files, many more than they need. The reason this happens, I think, is that you think every part should be unique, and so you use 1 and 2 and 3 and 4 and 5 and 6 and so on. But if the disorder that you're trying to model is in a different region of the structure, there's no harm in using 1 and 2 over again. You're merely using that as a separation of disordered components, and they don't have to all be unique. But if you are using a free variable, then they do have to be unique, because let's say you have something that's like part 1, and you assign a free variable to it so that it can refine the occupation of that part, 21, and then maybe part, then a bunch of stuff, and then part 2 minus 21. So the sum of those two parts adds up to 1, and the 2 refers to the free variable that appears after scale in the FR line, right? And then this would be, say, a starting value for this part. It could be anything you want. It's going to refine. It's a variable. It's a parameter. And then, later on you might have part 1, part 2 again. But you're using a different free variable, so maybe 31 and minus 31. You can still use 1 and 2 here, but these are in a different location on here. They're going to be here. Say something like that. If you don't want them to add up to 1, but you want them to add up to something else, like a half would be typical. You would add, so these add up to 1. If you use instead 20.5 and minus 20.5, those are going to add up to a half. It's just the way that the program was written. I know it's a little confusing. It certainly confuses a lot of people at the beginning. But I think I uploaded the GelX guide that originally talks about this, and also the the PDF file. If you go to part, it explains some of this too. And don't forget that you have to end with part 0 to cancel out this part stuff. Otherwise, you're going to be refining the rest of your atoms with the wrong occupancies. Yes?
You have to give that 8 parts. Then what to write after minus 9?
It just becomes 101. So you go from 91 to 101. It's just the 10th free variable, and then the 11th, 12th, and so on. And if you start to exceed this line here, because you have so many free variables, don't worry about that. You can just, on the second line, at the first end of the first line of things, goes on and on and on. And then you start to get too long of a line because you're violating the 80-column thing. You can just put an equal sign there. And then the second line continues. I usually put 4 spaces at the beginning of the second line, just to make sure that the syntax is right. But you can just continue. You can always do that. It's just the equal sign is just a continuation, like when you have the anisotropic thermal ellipsoids, you know there's always an equal sign at the end. So that's continue, okay? And then a really quick and dirty way to go backwards from anisotropic to isotropic is to just delete that equal sign, which you can do with the replace command. If you get rid of the equal sign on an anisotropic thermal ellipsoid, it will go back to isotropic. So that's one way you can do it quickly. Oh, okay, let's go to the first slide and then I'll remember what else I wanted to say. Okay, that's on. Okay, well I didn't I didn't actually write it here because I knew I would be writing it on the blackboard. So the basic syntax is just part, number, site occupation factor. If you don't want the site occupation factor, leave it off. The default will just be 1. Okay, but it's a really easy way to assign the same site occupation factor to a list. Everything within that list will have the same. And let's say within a part you've got a carbon which later you want to add hydrogens to. If you add the hydrogens using the hfix commands or the hadd command, for example, it'll also add the correct site occupation factors. So that's one reason to add the hydrogens later, because then it'll automatically be given the right site occupation. Okay, any other questions about that aspect of it? I want to talk about part -1 also, but just the general part thing. Just remember to always put the part 0 at the end. Don't forget that. But if you're just going from part 1 to part 2, you don't need an extra part 0 in there. Every time there's a new part statement, it cancels out the previous one. Okay? Okay. So what about part -n? Usually this occurs when you have disorder. And same here. I mean, these are usually disorder situations when you have the different parts. But this part minus is special for when the disorder occurs near a special position. So a position where there's site symmetry. And the reason you do it is that you don't want to be double counting the atoms that are part of that disordered site that's near the center of symmetry, say, or center of a twofold rotation, some other special position in the structure. And you can have even more than 2 things there. They don't have to be the same thing, but usually if it's near a center of symmetry, they are the same thing. Usually, not always. You can have a benzene and a chloroform on top of each other very easily in a structure. That's common. So you've got actually 2 different kinds of molecules, but it could be 2 different orientations of the same molecule, like 2 toluenes that are disordered. That happens a lot. Now, there's no limit to the size of the thing. It doesn't have to be a solvent molecule. Like I showed you a whole molecule disorder in one structure where the whole molecule was disordered and they had to be parts. Extreme example is with fullerenes, which happens a lot, and that happens to be what I do a lot of work on. So I'm going to show you a special case with fullerenes, and also another way that I want you to remember how to count up the number of atoms correctly so you get to the correct values in the unit statement. I realize that a lot of people don't get that right. I see it all the time, that the unit statement has the wrong number. Either the unit statement or the Z is wrong because you're not counting up the atoms correctly. So I'm coming to that. Okay, so this is a structure that was done quite a while ago by Brandon Mercado, who was my student at the time. And this is a fullerene with scandium oxide inside. But it's very common that this occurs. Fullerenes like this space group, C2/M, and we see it over and over again. The problem with it is that with the mirror symmetry that occurs in this space group, and the fullerene usually sits right on top of it, but does not actually have mirror symmetry in its position there. It's usually rotated away from the mirror. It could have a mirror, say, this one could. You see there's a mirror that goes through it, but it doesn't sit on the mirror. It's actually skewed with respect to the crystallographic mirror. So what does that do? It means that you have two on top of each other because the mirror symmetry is still obeyed crystallographically. Let me show you the next picture, and I think that'll be clear. Okay, so Brandon made these pictures, but I think they display what's going on pretty well. You look at your difference map, and what you get is this mess here, because the asymmetric unit is actually just half of the fullerene, and it looks like all of the carbons are just on top of each other. So your job is to grow that, to utilize the mirror symmetry, show the other half, and then pick carefully the correct ones that make a reasonably connected fullerene molecule. It's tedious, and it's one reason why we actually build these models with plastic snap-together things so that we can look at the thing while we're trying to do this. So this is one orientation, and now look, see, this is where the crystallographic mirror resides, but you can see that the carbons are offset. They're not on that mirror. So reflection must occur, though, crystallographically. So there's a whole other set of 82 carbons that's on the other side of the mirror. And so when you put them together, so this is the second orientation. You put them together. He's color-coded it, so you can kind of see the blue and the red are the two different orientations superimposed. But until you sort them out and figure out which color belongs to which ball, you're looking at a real mess. It's a challenge. So how do you do this? You have to, again, use the part minus statement. And in this case, each occupation is a half. So it's part minus 1, 10.5. For one whole list of 82 carbons, you don't have to write the other list of 82 carbons because it's generated by symmetry. And because it's easier to deal with just one set of 82 carbons, that's what we do. So that's correct to do that. So what does it look like? In the ins file, you just have a long list of carbons up to 82, and then it's part minus 1. And before this was written, the 10.5 was added there to get them all to have half occupancy. All right, you see you're staring at that. So how many C82s are at that site? A half of a C82 or a whole C82? So this is where I want to, okay, don't go to that yet. Talk to you about adding things up. So again, this doesn't really make a very good slide. So let's say you have some disordered things that are in part statements. Like you might even have, say, an iodine that's disordered, and then you've got, it's X, Y, Z. And maybe it's something like you've modeled it 10.4 in some thermal parameters, and then you have another iodine, let's call it 1. And say this is 10.3. So they don't even add up to 1. Use. But then you've got a lot of other atoms that are full occupancy. But something happened to the iodine, I don't know, it got oxidized, it left or something. Or maybe there's another one somewhere. But how do you find out what the actual formula is so you know what the Z is? Because the Z is the number of formula units. So how do you know the formula? Sometimes it's really tricky to figure this out. So my approach to this is to look up how many general positions there are in that space group. Not the special positions, but the general positions. Like, for example, the space group C2 over C has 8 general positions. P21 over C has 4 general positions. So if you look, this is another trick too, is to look in the LST file. The first part of the LST file contains all your input atoms, and then towards the bottom it contains the output atoms. And in that list, the occupancies are listed not as 21 and minus 21, but as the actual refined values. Have you noticed that? In the LST file, the second set of positional parameters gives you all of these occupations. So that gives you the final occupancies of everything. So take those occupancies and the atom types that they belong to and multiply by the number of general positions. That's a fail-proof way to get the number of atoms of each type in the unit cell. Unit cell. Okay, now you know how many are in the unit cell. You can divide it up into your molecules, however you're defining the molecules, you know. So that number, multiply the sum of all of these by the number of general positions, is going to equal what should be in the unit statement, and it also tells you how you can divvy it up so that you figure out how many molecules are in the unit cell and give you the Z value. So the Z might be the number of general positions, but if you have things that have molecules that have symmetry, then it will be less than that. Because, yeah, the symmetry is generating the other halves or fourths of the molecule, whatever. All right. The LST file also, of course, after you've said ACTA, gives you what you've put in the unit statement and what is actually there in the units, should be in the unit statement. So that's another double check that you get it right. And if all else fails, when you do checksif, SIF, it will complain. The problem with checksif is it doesn't know how you are defining your molecule. So it may disagree with what you've given as the Z value, especially if there's symmetry in it. Don't worry about that. You're the final judge of what Z should be because you know how you define the molecule. Okay, so checksif may disagree with you, but if you're sure that that's how many of your molecule is in the unit cell, then stick with that. And this error only really comes up if there's symmetry. Okay, so do you have questions about part? Now, I gave you a couple of references for using GelX, so read those again, and if you're confused, see what you get. So many things to learn. Okay, so these are the answers to the structures that I gave you. And so if you do want to just play around, you love solving structures, these are the answers, these are the molecules. I have done this in the classes that I've taught where I'll give maybe a dozen different structures that you can practice on. And some students do one, and some students do all 12. And those are the students usually that end up doing crystallography because they love solving structures. They didn't hear me when I said just do one. They did all of them. Okay, so this is the first one. It was called HK3785. And I just did a quick drawing of it. There's really nothing too difficult about this one. Remember, though, when you have a methyl group, if it behaves well enough, use HFix 137 and not HFix 33. This was 137 because it's nice data, and it can refine the methyl group according to the difference Fourier map. Okay, this one was MA10. This one is actually on a symmetry position. So you only have half of that as the asymmetric unit, and then you grow it. So here's your question. Does this have twofold or mirror symmetry, this molecule? What do you think? How many people think it's a mirror? Raise your hand. Mirror? Okay. How many think it's twofold? A little bit more. A lot of people are still staring at it. It's a projection which shows the symmetry, but it's really hard to tell which it is. I agree. I mean, if I had done better depth cueing on it, you would probably know right away. But you can tell, if you can tell what the symmetry operation is that generated the other half, and I can tell very easily, like in XP, and in fact, every program, it's going to give you the symmetry operation, but you usually don't pay attention to it. Here's a simple rule of thumb is if two of the positions are changing sign, it's twofold. It's a twofold rotation. If only one is changing sign, it's a mirror, because it's just reflecting, right? So this is a key to tell you that it's a twofold. So O1 goes to O1A by a twofold rotation down. It's down here, okay? And O2, O2A, again, it's rotation. CL2, C1A, rotation. Yeah. And I applied the rotation to the whole structure. I didn't just apply it to this. I applied it to the whole structure. So this also is generated by the twofold axis of symmetry. Otherwise, it looks kind of asymmetrical. So I did it to the whole structure. Okay. This one has an intramolecular hydrogen bond. So if you have worked on this one, see that you actually define that hydrogen bond, that you find it. You should be refining this hydrogen here, the one that's involved in the donor side. And then you get an ESD on this distance, and then of course on this distance, and on the angle. And then this hydrogen bonding should appear in the CIF if you did it right with the HTAB command. Okay, that's about all I have to say about that one. This one doesn't have anything really special about it. It's a nice structure. I plotted it without the hydrogen atoms because it did look pretty cluttered with the hydrogen atoms. That's an option, of course. I think most people could figure out where the hydrogen atoms go. Then again, this one was plotted in Mercury instead of in XP. The other ones were in XP. So you can see what the Mercury graphic will look like. Put the hydrogens back. There is a molecule of, I didn't do a dash line, but there is a methanol in this one. So there is another hydrogen bond here. Could have been dashed to show that. So this is intermolecular hydrogen bonding. Okay, beautiful. And I think there was also hydrogen bonding across here. I didn't recheck it, but there usually is when you have a carboxylate group like that. You get this sort of dimer, carboxylate dimer of hydrogen bonding. It seems that dichloromethane appears in structures a lot, partly because we use it a lot. Chloroform also appears a lot, and that's in part because it has a pretty acidic hydrogen on it, more acidic than in dichloromethane. So it often is involved in some kind of a interaction, weak, non-covalent interaction with other things. Good solvent for sort of polar compounds. Yeah, not much else to say about that either. So that's really all the time I had to make this slideshow. So why don't you think about things that are still unclear to you? Please ask me, and let's talk about it. Overwhelmed? Why is it when we end the lecture, people come up and ask me questions? Don't be shy, just ask. It makes it interesting for other people. Tell me what you do when you can't solve a structure. What do you do? What's the first thing you do if you can't solve a structure? Do you look for a different space group? Do you ask your friends? Do you try another method? Has anybody ever used SIR, S-I-R, to solve structures? This is built into WinGX. Sir, does it work? Yeah, usually works, I think. Yeah, that was one of the really powerful structure solving methods. Had many versions. I think for me, the most difficult structures are the ones that don't have any organometallic components. They're just all metals, or no carbons and hydrogens. It's always reassuring to see a ring or something like that. So, my advice is, do look at the space group. Make sure that when you ran XPrep, there weren't a lot of suggestions for the space group, and you may have picked the wrong one. So go from whatever symmetry you have to lower symmetry. And in particular, that is often a good idea if you're collecting data at low temperature. I haven't spent any time on the effects of doing that, but time and time again we find that the structure at low temperature has a lower symmetry space group than the one at room temperature. So you get what's called an order-disorder transition, where the ordering is actually the one at low temperature, disorder is at room temperature. For some reason, this is often true. And at the same time that you get that transition, you often introduce twinning. So while the low temperature structure can look much better than the room temperature structure, there may also be a twin law that needs to be applied. And that's when Platon is very handy. You can just put it into Platon and say, twin rot mat. It will find the rotation matrix for you. Oh, I didn't mention this before either. Yesterday when we were looking at Platon, and you put your CIF and your FCF file in, and you check on this twin rot mat box. Twin rotation matrix. One option was to output the HKLF5 file. Do you remember I did that yesterday? But there's another option, which is just to look at this matrix, which is just a set of 9 numbers. It could be something like 0, 0, 0, minus 1, 0, 0, 1, minus, let's see, 1 sign change, 0. Okay. So this matrix would be, oops, I'm missing 0, minus 1, 0. It would be interchanging your axes, but that may be all you need to do to get the twin. So in your ins file, keeping the HKLF4 file, not using the HKLF5, you just input this matrix as a twin, a line that says twin, and then you need to have a BASF line as well to give an estimate of the 2 different twin components. So you can start out with 0.5 if you don't have any feeling for that. So that may be all you need to do to really, really, really improve your R value. So this is with an HKLF4. If you use HKLF5, you don't need to put this line in because it's already taken care of with the batch file, HKLF5 file. Forgot to mention that. This also works very well sometimes. If you have ever used this program Cell Now, which is something else that Sheldrick wrote that helps you get the initial unit cell, this matrix is also given in Cell Now. So when you report a twin in the CIF file, it's a very good idea to give the twin law. You could say this, this structure was twinned as a pseudomerohedral twin or something like that with twin law. This and twin components being whatever that refines to. It sounds good in the CIF file. You'll notice too, if you do a CIF check when there's twinning, some of the messages will say, this doesn't apply because it's twin. Because some things can look funny with twins, but yeah. Sometimes you can actually figure it out yourself by just looking at the structure, but that's harder. It's easier to just do it by asking. To retain the right-handed coordinate system, if two of these change sign, then it's going to change the handedness. So you will see there will be an error message, and then you realize you need to add another negative sign. Don't worry about it. It's obvious that when you need to do that, because you're switching to left-handed instead of right-handed. Yeah? Okay, say that one more time. Uh-huh. Yeah. Okay. If you're looking at the graphical displays, which most of the programs have now, the thing I look at the most is the correlation one. So that's the correlation between where the expected spots occur and where they actually do occur based on the unit cell. So that's, it goes like something like 0 to 100, I think, or either 100 or 1, I can't remember. And then as you go over your frames, or your images, whatever you call them, it's going kind of like this, right? I'll keep an eye on that. You want this to be preferably more than a half, because if it's a half or less, you may have the wrong space group, for one thing, and it's just not very good correlation. So I like this to be, I guess this is 1. So this between 0.7 and 0.99 is the best. I've actually seen things at 0.99 where it's really strong diffraction and perfect crystal. That said, sometimes it's not that high. Sometimes it's more like 0.4. But if it's less than 0.4, I think you're very unlikely to get a very good structure. So the correlation, this is usually on the upper left-hand side, is called correlation. I would keep an eye on that plot. Another one I really like is the one that shows the spots sort of as an image, the spots themselves. And it's you want it to kind of look like it's centered in that box, but sometimes it doesn't look like that. It looks like more like, big blur and another one really close to it, or maybe even more. That's usually a sign of twinning or a crack or cracking in your crystal. So if it's cracked, you might need to fix the box size when you do the integration so that you actually encompass the whole thing. And there's another image in there, another way that you can look at this. While on the individual frames, there's a box that you can select, and it does a plot of the peaks. And ideally, it's going to look like something like this, with a pretty narrow peak width. But if you have this situation, it's probably going to look more like something like, so there'd be a little one, and then another one, and then another one, and another little one, something like that. It's not death. It doesn't mean it's not possible to solve this structure, especially if that's due to cracking and not something like bad twinning. If it's simply cracking, then you just want to make sure that you integrate the whole thing here. So this is like omega down here that's being plotted. So by adjusting the box size during integration, you can pick that all up. And another thing to do during integration is, if it's a really broad peak, too, you might want to consider fixing the box size so that you're always getting the whole thing. Because in some regions of reciprocal space, the spots may be broad, and in other regions they may be narrow. But in that case, I think it's better to use the same box size all the way through. So you can adjust it to a larger size and fix it, and that will also make things go faster, because all along as it's doing the integration, it's trying to adjust the box size. That was the way the algorithm was set. But in the beginning, when they first came out with the area detectors, the user had to fix the box size. It wasn't adjusted automatically. Anyway, you can try both ways. Is anybody using Apex 3 software here? Or are you just using 2, Apex 2 and others? Yeah. There is a new version of the program. It's called Apex 3. At first I didn't like it, but then I installed it and it actually works fine on older data sets as well. And they've done a good job on the programming so that it takes much less time to do the integration. It's much faster. So don't be afraid of Apex 3. It works. And for some unknown reason, they changed the names of some of the things that you want to do. You know, like, I don't understand it. So you look at the menus and you wonder, well, what is that doing? Because it's not what I expect to see. But then you get used to it. So I think these programs are written in Germany, and the Germans don't always pay attention to what we're used to for some reason. Stubborn people. So, anything else? Yeah. I'm sorry, I don't quite understand your question. Uh-huh. Mm-hmm. Mm-hmm. I'm still not counting what you're saying. I just. Okay. Maybe this is what you're asking. I'm not sure. Okay, let's say you have a benzene. You see in the difference map, it looks like this. And then you also see something that looks like this. Have you ever seen that before? So this might be a twofold axis, or it might be a center of inversion. But the point is that it isn't just sitting on one side. It's being disordered with respect to the symmetry position. And so this tells you right away that you've got disorder with respect to symmetry. I'm leaving off the hydrogens and everything. Just don't worry about those right now. So actually, this carbon and this carbon are used on both molecules, so those should have a site occupation factor of 1. But the rest of them are all not being shared, and so they should all have site occupation factors of 0.5. But in your file, you don't need to count these because they're generated by symmetry. All you have to do is count these that make one molecule and then set these to, I'm sorry, I said it backwards. These are at 0.5. No. Okay, they're at full occupancy because they used both halves. These are also, wait, let's see. I would probably put them all at half occupancy, all 6, sorry. So that would be part minus 1, 10.5, and then your 6 carbons. And then part 0. So you're just using these 6, and you're not using the rest of it. If when you do this trick where you multiply by the number of general positions and it doesn't come out right, then you didn't do it right. It's sometimes not obvious how you should do it. But here, I mean, you can see that the sum of this by some even number, like 8 or something, is going to give you an even number of benzenes. So that makes sense. Is that anything like what you're asking?
What are the things we actually look in the LST file?
I was just, for the LST file, I was just saying, look at the second set of atom positions together with their occupancies. For each type of atom, add up the occupancies, multiply by the number of general positions to see how many are there in the unit cell. And sometimes it comes out to not an even number, but that's okay. It's just what you've done. I mean, sometimes a solvent has evaporated from the crystal, so it's not at 100% occupancy. It's not even at half occupancy. It's something in between or less. Could be 20%, because it's basically just evaporated from a void in the crystal structure, and it's not there anymore. So I always really keep an eye on thermal parameters. If the thermal parameters explode, they get too big, then you need to reduce the occupancy. Too big meaning big related relative to the rest of the structure. They can be somewhat larger because they're jiggling around more than that big space, but they shouldn't be a lot bigger. Like thermal parameters that are 0.2 electrons per cubic angstrom are crazy. They're never that big. 0.2 is too big. There's something funny going on there. Some very large thermal motion or a lower occupancy. Going from room temperature to, say, 90 degrees, the thermal parameters are about a half. They really do become a lot smaller. Let me think. The R factors increase? No, not if you've done it right. They shouldn't increase. They usually decrease. Yeah, because by doing this, you're taking into account all of the scattering, so it should decrease. It should, yeah. What causes the R to increase is just an increase in the number of parameters, or something that's wrong. There is a distinction made between restraints and constraints. I don't want to go into that, but it's in the manual. Restraints are, some restraints are accepted better than constraints. Constraints mean you're really fixing something without allowing any variation. A restraint, there's always some leeway, and that's accepted better. Yeah? Say it one more time, I'm sorry. Still didn't understand.
The method that we use for solving structure, like a least squares or something.
For solving a structure, least squares is for refining the structure, but for solving the structure, my preference right now is XT, or shell XT. But if there's just a lot of heavy atoms and not any light atoms, I might actually use Patterson methods. And then there's all these other programs, like SIR and direct methods and shell XS, and yeah. They work, but it's going to be more of a long process of solving the structure. Like,
What is the difference? We use instead of LS, we use CGL.
oh, the CGS. That is somewhat obsolete, the CGS thing. I don't think I've used it for many, many years. The program can invert, now because of computers, it can invert very large matrices, and that was, I think, the main reason to use the CGS before. That you didn't have to it couldn't handle the parameters. But I think just regular least squares now is all anyone ever uses. Yeah, the CGLS was a kind of more gentle refinement, which didn't require inverting hard, big matrices. But it was slower, much slower. You don't have to do that anymore. You know, you can do least squares in less than a second now of pretty big structure. It's simply amazing. So the old methods where you use blocks and CGLS, that was just because of computer restraints. Good questions. More questions? What other problems do you encounter or did you puzzle over? See, I hope by doing just the command line stuff that it really does give you an additional insight into what you're looking for. Because I think programs like WinGX are great, except that you don't know exactly what it's doing. It's more mysterious. It's doing its own thing. Anyone else? Yes, okay. Mr. Question Man there.
Please tell us something about DAM 0.
Damn. Oh, okay. I never really use it, but again, you know, it was very useful when we had slower computers. But the I think you should read the latest GelX manual and see what it says. I think it's been superseded by some other commands like delu and simu and things like that. Especially delu, I think. Yeah. I've really never found an instance where I wanted to use damp. But the idea was, I guess, that if you had long chain hydrocarbon or something like that, it would help it to settle down. I don't know. Try simu and delu. Those are both really good for that sort of thing. I also did notice that there's an old manual and then there's a new manual that just came out. If you go to the homepage for GelX, it's there. The manual isn't as inclusive as the old manual. So it's a good idea to have both manuals. So I hope are you all able to access this place that Sankar set up for the things? So I have a bunch more things to give you, just haven't had a chance to trade them off. But I'll give them to Faraz and after today's class, and then he can give me back my thumb drive tonight, hopefully, and everything will be there. So I've made PDFs of all the lectures that had PDFs, and a bunch of other things which I think you'll find hopeful. Some websites that you might want to go to, some manuals that we have PDFs for, like the CIF manual, for example, GelX manuals, some references, that sort of thing. And, you know, I'll be back in Davis in a couple of weeks, but if you still need some help, I don't mind it if you email me occasionally. Anyone else? Okay, so this afternoon I'll tell you some more about the light sources, the synchrotrons. At least that. I'm not sure that's going to take an hour, but I might think of something else to talk about. So I hope I'll see you this afternoon. That'll be our last class. Okay? All right.